recording on this computer, and then I want to share my screen with you, and I want to run this as a presentation. So, good afternoon, everybody. I hope that you're still doing good. And in Boulder, we have snow, so I suppose that you're all locked at your homes safely, not interacting with anybody, keeping the curve down, and so on and so on. Today, we are talking about my favorite topic, and actually about a mixture of all my favorite topics. And these favorite topics are magnetic field estimation, and then inference and fitting, and the Markov Chain Monte Carlo finally. So this is really all the merging of all the things that I like to do the most. So before we start with everything, I'm just going to go very, very, very quickly over the theoretical foundations for what we want to do. And what we will start with today is we're going to pick some Stokes profiles from HINODE data, and we're going to try and calculate, estimate, or infer the line of sight magnetic field using something called weak field approximation. So I already put the slides online which describe you what weak field approximation is and basically derive that. And people who attended the course last year maybe remember that we derived that. I wonder, does anybody remember how to, not literally how to every step, but what's like the rough idea about showing that the weak field approximation holds? Does anybody remember that? Yes, no. Well, okay, technically it's only Niraj and Momo. So okay, what we discussed last week is we talked about a polarized radiative transfer equation, right? And one of the assumptions there was that the emission is unpolarized. I told you that later we can abandon that once we start treating, for example, scattering polarization, where the atomic orientation and alignment in the upper level can create polarized emission. But in principle, what we have is we have this equation here, which I'm now writing in context of tau, right? And so I don't pay attention to this bottom eta 0, so forget about the eta 0 now. So here we have a radiative transfer equation, which is written as basically it explains you how the Stokes vector changes with depth. And this matrix here, that looks a little bit like Miller matrix, is in this context called absorption matrix or absorption tensor, right? And for example, interesting components of this tensor for us were eta I, which describes valence dependence. So basically, these tell you something about the valence dependence, right? Because you see that various profiles are participating here. And when we look at this eta I coefficient, we see that it consists of 3 profiles, right? And these 3 profiles are the absorption, or if you want, emission profiles belonging to sigma plus, sigma minus, and pi components of Zeeman transition, so which means the components which correspond to the change of angular momentum of 0, +1, and -1, respectively. And there is also a factor theta, which means that the orientation of the magnetic field influences how these individual profiles are being combined. Right. And then for eta V, which describes basically coupling between Stokes I and Stokes V, which you can see from this matrix here, in the eta V, so it basically describes the coupling between the circular polarization and the total intensity of the light. You have these phi minus 1 and phi plus 1, which basically just come from these 2 transitions which create photons where the change of magnetic number m is +1 or -1, which means circularly polarized photons for us. So now if we assume, and I already showed this to you previous week, so I'm going to run through this really, really quickly. If we now assume that all the other components are 0, and for example, they might be 0 because the magnetic field is angle theta here could be 0, so magnetic field could be completely oriented toward us. And in this context, we're going to understand that we are only modeling the parallel component of the magnetic field, the one that is in the line of sight. And if we do that, then we only have these components remaining, and I can write this as 2 coupled radiative transfer equation. Why are they coupled? Well, because on the left-hand side, we have the derivative, which are separated, but on the right-hand side, we have I and V in both of the equations. But don't be surprised. What we are going to do is something that we do very, very often. We're just going to We're just going to add and subtract these things, and then what we are basically going to obtain is we are going to obtain two radiative transfer equations, where one is the radiative transfer equation for I plus V, the other one is for I minus V. Source function. Yeah.
So what is this optical depth in all these equations? Is it just?
So in this context, this is some referent optical depth. As you have seen, I didn't make it wavelength dependent. So this is optical depth on whatever wavelength we chose to be representative for us. Usually in the radiative transfer codes, it's wavelength at 5,000 angstroms or something like that. So in that context, if we use the optical depth here on the left-hand side, then these etas are basically dimensionless quantities which are wavelength dependent and which tell you the ratio between the opacity at that wavelength with respect to this referent opacity, right? So if I was looking at 5,000 angstroms where there are no lines, which is equal to my opacity in the continuum, then all these diagonal would be 1, 1, 1, and there would be no off diagonal elements because they would all be zeros. Does it make sense? Because there are no spectral lines, so it has to be 0.
Yes, I was just a little bit confused because when we integrate on a scale, on like a 500 scale, if it's numerically gonna be stable enough to do it for a spectral line, which might be, what I'm saying is if the grid has the required resolution at the required place.
The grids usually do have required resolution, because even though the spectral lines can be much more opaque than the continuum, the ratio between the line and the continuum doesn't change so much. So what you need to ensure is not that you have the needed resolution, it's just that your atmosphere reach is high enough, right? And that's, for example, when you look at the FAL-C model, it goes in the optical depth from, let's say, -8 or -7 in log scale to 1.5 or something like that. But of course, to model, and that is continuum optical depth. But of course, to model the continuum, you don't need to go so high. But since you have the lines which are 10 to the 5 or 10 to the 6 even times more opaque than the continuum, then it's still going to cover their formation regions. But if you, for example, want to model Lyman alpha, you need even higher atmosphere. So -8 is not high enough. Is that what you were asking?
Yes.
Yeah. Okay. So, but I mean, now we are not talking about, there is no numerical integration here. This is all analytical for the moment, because now when I do this adding and separation, you see that I have this eta I plus eta V and eta I minus eta V. And if we go back to their definitions here and assume that theta is 0, then what I'm going to get is I'm going to get 2, in one case I'm going to get 2 phi minus 1, in the other case I'm going to get 2 phi plus 1, right? Because the other ones are going to cancel. So you can verify this on your own. And and then basically what I have is I have that eta I plus eta V obeys the radiative transfer equation, which is in a way shifted toward red. In the other case, the intensity is shifted toward blue, right? So I can make mu notation and I can call them I red and I blue, right? And when I solve these two radiative transfer equation, what I'm going to get is I'm going to get one spectral line that is shifted a little bit to the red, the other one which is shifted a little bit to the blue because of the profiles, right? And the shift is going to depend on the magnitude of the magnetic field, on this delta lambda B that are we going to call Zeeman, let's call it Zeeman broadening or Zeeman shift, if you prefer, right? And then what I can do is I can write this I plus V, which I'm calling I red, which is actually I0, which is shifted by delta lambda B. I can write it through the derivative of the unshifted profile, right? So this, look at the last line, and now look at the, let's see, there is mouse, but mouse can't mark this, so try to pay attention to the mouse. So this term here is the Taylor expansion of this expression here, right? So the assumption is the following. I have my shifted profile, which is actually, I have my IR profile, which is identical to the original profile, just shifted. So I added this minus delta lambda b here. And then I will write this using Taylor expansion. And if I do this for both I plus v and I minus v and subtract to find v, what I'm going to get here is I'm going to get something like this. So v is going to be minus di0, which I'm going to assume that is my intensity profile, over d lambda times this delta lambda b. And delta lambda b is a constant which depends on, so let's see, it depends on the magnetic field magnitude, line of sight magnetic field magnitude, valence squared, and this g, which is a Lambda factor. So the way that we are seeing that is we could say that in weak field approximation, and basically weak field approximation rests on only one assumption, and that assumption is that this Taylor expansion up here makes sense. Okay, so basically the only requirement for weak field approximation is that Zeeman broadening is small. And in practice, what it means for us, it means that Zeeman broadening or Zeeman splitting is smaller than Doppler broadening. But then later, when you do the experiments with this, if you want to use it, you see that it reaches much higher, and I have that it actually covers reasonable amount of magnetic field strengths. And actually now on our course webpage, I have posted paper by our colleague Rebecca Centeno, who explored the applicability of this weak field approximation for magnetic field measurements from calcium 8542, which might be interesting for some of you, So basically, what I want to emphasize here is that when you assume this, when you use this approximation, you will get that Stokes V is a linear function of di over d lambda. Okay, and that the slope of this linear relationship is proportional to the magnetic field, and that from the slope of the magnetic field, from the slope of this relationship, I can find the magnetic field. So what are we going to do now is we are literally going to do that. Yeah. So we are going to take HINODE data. We are going to consider these two lines, first one, then the other. One of the things here, and why these things are very limited, is you can only look at one spectral line at the moment, right? If I use two lines, then I have different lambda factors, and I cannot reconcile these things. I mean, in principle, I could use some mixed models or something like that, but it's much more complicated. It's much more easy to just analyze data sets for two separate lines. Okay, so then we're going to find the lambda factor of these lines. I'm listing them here. These are 1.67 and 2.49. So these are relatively large lambda factors. Okay, so lambda factor of 1 is sort of moderate. Already everything larger than 1 is interesting. Lambda factors larger than 2 means that lines are very sensitive. Strongest lambda factors that I know of, I think there is one line which has 4, and then there are some lines, for example, the lines, the iron lines in the infrared, one of them has lambda factor 3, if I'm not mistaken. So that's really, really sensitive. And having large lambda factors means that your lines are more sensitive to the magnetic field, means that you will get more circular polarization for a given value of the magnetic field, means that you will be able basically to detect and measure smaller magnetic fields. And this is literally everything that we need. So we need to know this relationship, and we need to know some constants for our lines, and that's everything that we need. And now we're going to do that. And I already did something like this with you last time, except now we are going to, okay, my earphones were broken, so I was browsing about that. Let's zoom this a little bit so that you can see this nicely. I hope like this is okay. So we already did this last year. So today I'm going to show you some new things. And basically what we are going to talk about today is how to estimate the noise from your observations using just the observations, so not knowing what the setup was. And what we are also going to do is we are going to use Markov Chain Monte Carlo sampling to infer uncertainties of the parameters that we are inferring. And I'm going to show you a very, very interesting and very useful package for both running these samplers as well as visualizing the data. Okay, so in addition to our usual, let's say, header of our Python files where we import matplotlib, numpy, fits, and so on, there are two new packages which I asked you to install. One of them is called MC, and it's the package for Markov Chain Monte Carlo sampling. I'm going to show you now how it works. And there is this corner, which is a very small package, which allows you to make super nice and super convincing corner plots. And corner plots are something that I have also shown you last week. These are these sort of scatter plots that show you the projections of your chi-square surface, actually of your posterior. And you can use them to see if your parameters are maybe degenerate, to see correlations between them, and so on and so on. Okay, so let's, we're going to do it the same way as we did last time. So I already have the notebook prepared, and then we're going to go through it, but occasionally we're going to change something and add new stuff as we go through it. And I think also today I'm going to give you some free time to basically to try some things on your own. Yeah, by the way, I just want to announce this now. I had a very brief power cut today at my place. So if I just run offline, don't worry, I'm for sure going to come back in a couple of minutes. I don't know why that happened, and I see that my my light is now blinking suspiciously here, but I hope that everything is gonna go fine. Okay, cool. So let's run this. Yes.
When you write the magnetograph formula that way, you assume that you don't have any longitudinal extension of the field, right?
Yes, this is only for the well, let's go back.
Radial.
Only for the radial, or what I would call here line of sight. Yeah, exactly. Yes. So here is a small reminder, and so on and so on. So let's also execute that, and we're gonna open this. I'm gonna zoom a little bit more. So we're gonna open this file called HINODE network C. C stands for corrected, because I had to do some correction of the data. Whoever is interested in using HINODE data, just get in touch with me. I'll tell you what little touches you need to make to it, so it's completely usable. And you can literally run this. Just remember to change the path according to your own folder. So we're going to load this, and you see that the size of this is 512, which is a typical size of the slit in. So this is sometime 2012. So 512 was a typical size for the slit at that time. On the other axis, there was 873 pixels, which means there were 873 slit positions, and then we have usual 4 for our 4-Stokes parameters and 112 for our wavelengths. And what I'm going to do is I'm going to plot continuum intensity map, which you can see. I mean, you know how to do it. I just say Stokes component 0 and wavelength index 0, and we get this nice plot here. And we see that this is a quiet sun with a couple, I would call them small pores or something like that. And the point is that we can't really see where is the magnetic field here, right? So from the intensity image, we cannot see where the magnetic field is. However, because we are going to do the proper inference today, first we need to see where the magnetic field is so that we can choose a pixel which has magnetic field in order to measure it, right? The other thing is that we actually need the wavelength grid. And I have shown you in a hands-on few weeks back how to estimate the magnetic, how to basically do rough wavelength calibration yourself. Luckily for HINODE, we don't have to do that. So what I actually suggest is you download this other image, which is one of the individual slits of HINODE. So I also uploaded there, and then you can print header using this command here. And then when you print the header, you're going to get a lot of data, which is let's make this nicer. Okay, you're going to get a lot of data, and that data includes a lot of things, from very starting default information like dimensions of axis and so on, manufacturer of the camera or stuff like that, to some details related to observations that we want to take a look at. What is important for us regarding HINODE? There are these two values. So CRPix1, which is 56.5, and CR value 1, which is equals 6,302.08. So these two correspond to the index of the pixel. And I know it sounds weird that we have a half a pixel, but that's the way it is. This means that that wavelength 6,302.08 is located at pixel index 56.5. Okay, so then the only thing to create the wavelength calibration, we need to know the sampling of HINODE. And to do that, what you can do is there is there is a link here, which if you click on it, takes you to HINODE guide. We need to wait a little bit for it to load. And then you maybe remember some of the names, who were the authors of these things, and then you can look for SOT. So there is SOT instrument guide, and then you want to go to spectropolarimeter, which is at page 17. If you go to spectropolarimeter, there it is, and it says that spectral resolution is approximately 21.5 milliangstroms. That's an error. It's actually not the spectral resolution, it's the sampling. Spectral resolution is slightly poorer than this. So yeah, I mean, this is not the best. Obviously, this is not the best expression. It might confuse you, but trust me that this actually tells you what the sampling is. So now, when we need the sampling and we know we know the point, the position of at least one pixel, we can create our wavelength grid using something like this. And I actually don't need this print because I'm convinced that it's okay. So basically, I'm going to create yeah.
Is the difference between the resolution and the sampling the factor of 2?
It should be, but for HINODE, it's not. So in ideal case, if your resolution is, let's say, 20 milliangstroms, your sampling should be 10 milliangstroms in order to resolve these smallest scales according to, what's the name of this? Nyquist sampling theorem, right? However, for HINODE, they chose to slightly undersample their data. So resolution of HINODE is something like 30-something milliangstroms, while the sampling is 21.5 milliangstroms. So yeah, I don't know why is that, and maybe if we do numerical experiments, we can see that it's maybe to do reliable inversions, it's not necessary to have really things sampled according to Nyquist theorem and so on and so on. I mean, keep in mind that very often we are very rarely going to really deconvolve this data spectrally or something like that. We're usually just going to account for this finite resolution in our diagnostics codes, and then we can take a look at that. So in principle, what I should do here is I should take into account for this broadening when I'm doing the fitting to really get real magnetic. Or actually, no, because it's going to cancel between V and. We should think about this. Try to think about this, and let's see the process, and then we can discuss that. But in principle, it should be, but it's not here. Okay, so now we have our wavelength, and let's just plot one spectrum to take a look at it. This is something that you have done many times. Here is spectra these are the indices down there. I'm not using the wavelength yet. These are the counts, so everything is fine. The reason why I did this is I want to see where is the index where my line wing is. Because you remember that if Stokes V is proportional to the derivative of Stokes I, then the peak of Stokes V should be somewhere in the middle of the wing of the Stokes I. So I roughly estimated that this index is roughly 23, just by my educated visual guess, and I'm plotting here now the image, which means I'm plotting the Stokes parameter at each spatial point. Stokes parameter 3, which means Stokes V. At wavelength point 23, and I'm dividing it with the mean continuum, okay? And when we plot that, we're basically going to get Stokes V map in the blue wing of 6301, and this is already beautiful. This already tells us where the magnetic field is, because magnetic field is creating the circular polarization, and now we see what is happening. So now what I can do is I can choose one of the points, and I roughly somehow estimated that the roughly points with indexes, keep in mind that Python reverses the axis when you plot like this. So we had the point, I somehow concluded that if you have a point with indices 250 and 700, you are somewhere where the magnetic field is. So I'm plotting now Stokes I and Stokes V for this point. We're going to change the point indices later, and we can look at various points, or we can even interpret chunks of this map, and etc., etc. Okay, and now if I plot Stokes I and Stokes V in this point, they look like this, right? And first thing that I want you to pay attention here is that the magnitude of the Stokes V is significantly smaller. So here I have something like 30,000 counts. Here I have 1,000 counts or so, which we know, right? We know that unless there is something really extreme happening, we know that circular polarization and especially linear polarization is very small, right? In fractional sense. Right. So let's check if the derivative of Stokes I really looks like the derivative of if it really looks like V. So I'm going to use this very convenient function here called gradient, which calculates these derivatives for me. So I'm literally just going to make this new variable called di over dl and call it gradient and say that it's gradient of Stokes I in given point divided by gradient of Stokes, divided by gradient of Wayland. And gradient of Wayland is basically constant because the grid is equidistant. And then when I plot that, I get something like this. And keep in mind that I'm taking into account minus, so I'm plotting minus di over dl, just because, well, I don't know, just because this way it's also easier to see that these things really look like each other. Okay, so probably now if I mix these and show them to you, you would be like, oh, okay, wow, which one is which one, right? We can see which one is which one because of the magnitude of because of the amplitude here. Okay, cool. Well, now let's calculate the magnetic field from this. So as we said, Stokes V is directly proportional to di over d lambda, which means that the relationship between Stokes V and di d lambda should be linear. And we're going to start doing that just using simple matrix inversion. And I'm just going to remind you that for linear models, we can literally, we don't have to do any fitting, we don't have to do any minimization, we can just solve linear system of equations. So before we start doing that, let's just make a scatter plot between di dl and Stokes V. Except I'm going to do it I'm not going to do it for the whole wavelength grid, I'm just going to do it for the half of the wavelength grid, because if you remember the equation, and what I told you before, we have to treat the lines separately because they have different lambda factors. So slopes of this linear relationship are going to be different for 6301 and 6302 line because they have different lambda factors. So if I plot this scatter, it looks something like this. Okay. Obviously, there is a lot of points, you know, around zero because a lot of points are in continuum. And these points have no gradient and have no Stokes V, right? So in principle, if I really wanted to, I could cut off a bit more here. I could do like, I could also cut, for example, first 10 points. And then I have a little bit less points around zero. And I can maybe even do, I can maybe go to 50 here. So now it's a little bit more uniformly distributed. Why I'm doing this? I'm doing this because if I have a lot of points around zero, they're going to take a lot of weight, right? Imagine if I have a lot of points here around zero and just one outside, then the fit would basically ignore that one. I mean, it wouldn't ignore that 1 point, but the points in the middle would take much more significance, so to speak. So now let's remember how to cast this as a linear function now. So basically what I have is that this relationship is something linear. So let's say kx plus n equals y. But now my unknowns are not x and y. My unknowns are k and n. Okay. So if I wanted to write this as a matrix equation, what I would have is matrix equation which has two columns. First column are the values of x, second column are all ones. Then that matrix is multiplying this vector here, which has only two components, k and n, which are unknown, and that is going to be equal y, which are also known quantities, which is basically my Stokes V. So if I want to cast that this way, and now what I'm gonna do is, so we have 40 now. So we're going to cast this as a linear problem. So I have 40 data points, right? And these data points are, so we said from 10 to 50 here. And here we have 10 to 50. So what I'm doing here is that I'm making a matrix with dimensions ND2. First column are values of X, which means DI over DL. Second column are lower ones. B is my right-hand side. These are the values of Stokes V, okay? And then how am I going to solve this linear system? So this linear system is overdetermined. Well, we're going to solve it in the same way that we were solving the linear systems when we were doing the demodulation. And that's using, what was the name? Something Penrose pseudo-inverse. Does anybody remember the name? Okay, I honestly don't remember. You can look it up later. So what I'm going to do here is I'm just going to say, well, I have this pseudo-inverse, and then my solution is going to be what? Let's write a segment. Let's write a segment here on that. So let's expand this. So we have an overdetermined system, which looks like X equals B, and we are solving it using pseudo-inverse, right? Then I'm going to do something like this. Basically, to solve this, I have to multiply everything with the pseudo-inverse, and then when I solve that, I'm gonna get some values for my coefficient and intercept. Okay, and the way to check whether this fit makes sense is to replot this linear relationship, and now to add di over dl, except now I have to change my ranges. So from 10 to 50, here from 10 to 50. I probably should have named these variables differently, but it's fine. And we plot this, and wow, there is really a linear fit here. Okay, looks good. So we managed to fit the data with something linear, but what we don't know yet is what is the magnetic field. Well, we find the magnetic field from the relationship. So the slope was what? Minus 4.69 times 10 to the minus 13 times magnetic field. This is perpendicular magnetic field. Sorry, yeah, this is parallel magnetic field. So I'm going to call it BP, for example, times lambda squared times lambda factor. Okay, lambda factor is not 1.5, it's 1.67, right? And now what I do to calculate the magnetic field is I just do minus P, which is my slope, and I divide it with these constants. I print magnetic field, and in this case, it's roughly 150 Gauss. And this makes sense because if we go back, we're going to see that this polarization is actually very, very low. It's few percent, right? Intensity was 30,000. Stokes V in the peak was 1,000. So it's like 3%. And the magnetic field is very, very low here. So it's some 150 Gauss. So why don't we spend like 5 minutes just repeating this with another spectral line? So you basically just need to copy and paste this and change the valence. And let's do it just to see what's going to happen. So I'm just going to shut up for 5 minutes, and I'm going to start doing that. And you should just go ahead and do it on your own. And of course, in the meantime, you can ask me various questions. For the second line, I'm going to use even less points. Yeah, I don't actually need to do all this. I can just do the fitting. Okay. Okay, this is interesting. I chose the wrong limits here. So you probably want to you know, automatize this if you want to use this for some. Okay, here's the linear fit, maybe even a little bit better, maybe even more spread out lines. And now I'm going to calculate the magnetic field again. Except now we need to change the lambda factor, right? So keep in mind that the lambda factor is roughly 2.5, precisely 2.49. Then when we do that, we get only 108 Gauss here.
Change also the line.
Didn't I? I did.
Go down. You divide it by 6301.
Okay, but that's not gonna influence a lot, right? That's gonna determine, that's really small change in the wavelength, because it's almost there. So we are getting different numbers here. Well, there could be various things. It could be, I mean, obviously these are all low magnetic fields, so the values here are determined mostly by scatter and the amount of points that we get. So what you can do later is you can just try choosing different intervals and different width of the intervals in wavelength, and you're going to get different values of the magnetic field, right? So obviously the data selection here is sort of critical. And you might even want to make this very, very narrow to completely avoid any continuum and to see what is going to be the best fit. But in principle, also, I want to stress, when you use different lines, you're going to get different answers because of what we talked about last time, because of the formation height. So different lines are going to see, as we say, different magnetic fields. And in these sort of approaches, like is, for example, weak field approximation, or what I'm going to hopefully show you in the end, Milne-Eddington approximation, you are making some assumptions which are not true. So here we are sort of making assumption that there is only one constant magnetic field along line of sight. I didn't mention that on purpose before, but here we are only inferring one quantity, and the only way that we can, you know, attribute this quantity to something, we can say, well, this is the quantity where the line is forming, whatever that means. It could be that this point is maybe the peak of the contribution function. It could be that this point is where the response function to magnetic field is strongest, etc., etc. But the main point that I want to tell you is that the magnetic fields are going to be different if found from different quantities. So, okay, let's just rerun this once again to make sure that nothing is, yeah. Oh, sorry, guys. I'm so sorry. This was the wrong. Was this wrong? No, this was fine. Okay. Well, you can play with this later. What I want to move on is a little bit more serious and a little bit more thorough to do these things. In principle, we now sort of measure the magnetic field, but I have no idea now what my uncertainties for magnetic field is. I haven't taken into account, for example, the errors in my measurement, the noise in my Stokes V. If this is a very linear function, so there is only one best fit, but if I use something more complicated, there was no way for me to spot whether there are, for example, multiple solutions, whether some parameters are degenerate, and so on and so on. And believe me or not, in general, we might even not know the noise, so we might have to include the noise itself in the model. And I'm going to show you a very powerful technique and very insightful technique, which is called Markov Chain Monte Carlo, which is going to enable you to do all these things. And we've talked already about Markov Chain Monte Carlo, so this is going to be some method which walks through our parameter space, and our parameter space in this space is the space where intercept and slope of this linear function are living, and it's going to go through that, and it's going to somehow probe our values of the posterior, right? Because in principle, theoretically, remember that what we want to discuss is the posterior, okay? And of course, if we don't have any prior idea about the parameters, then we can say, well, okay, posterior, maximizing posterior and the likelihood is the same, but it's good to always think in the Bayesian context. So now I'm going to take a step back, and before proceeding, I'm going to define three functions, which are likelihood, prior, and posterior. So these are the functions which, given the values of the parameters and eventually the data, return the values of likelihood, prior, and posterior. Okay, so let's start from the prior because it's the simplest one, and I'm going to put it first now just in case. Prior is literally so this is the function which returns you which basically contains the information about the prior probability density function of your parameters. And we, for example, if you already did some analysis of some other data which involves the same quantity, you might have some prior beliefs how your parameters look like. But however, now we don't know anything about the magnetic field. It could be -1,000,000, it could be 0. As far as we know. Of course, it could not be -1,000,000. So what I'm going to do here is I'm just going to use this function here, which is called ln prior, and which, given the values of slope and intercept, always returns 1. Don't be confused with the return 0 that I'm using. It's because everything is in log scale. Okay? Cool. So then the next step is to calculate the likelihood. And log likelihood is basically chi square, right? And here I'm using the definition actually involving the standard definition of a Gaussian. So I'm just gonna add a comment here. Remember that Gaussian is P of x is 1 over square root of pi, 2 pi, sorry, sigma times exp minus x squared over 2 sigma squared, right? When you log this, you're going to get something like this. And remember that we log and then we sum, right? So the chi-square, so first of all, what I'm going to do is I'm going to calculate for these values of parameters, I'm going to calculate what the model predicts. We are using the linear function, so model predicts, so what model predicts? It predicts a linear function, which in this case looks like this. Y predicted, or Y model as I'm calling it, is parameter 0, which is slope, times x plus the intercept. Then I can calculate the chi-square, and this is going to be chi-square individually for each of the points. It's going to be model value minus actually measured value divided by the error, which is sigma. In my case, squared, right? Actually, it should be, yeah, no, this is all fine. And then, because this 2 is taken into account later. And then finally, what I have as my likelihood is going to be sum of -1/2 of chi-square. Then I have this minus 0.5 log 2 pi, which comes from this term here. And I have minus log of sigma, right, which is the error. So to make a comment here, error is sigma. And I'm doing this on purpose. So obviously error is something that, at least now, what we think is that we know in advance, right? When you do the observations, you measure your error somehow, and we're going to do it later. So, so in principle, all this part here is constant, right? So for the moment, I'm just including this. So the only thing that changes is chi-squared. So I can only compare the chi-squared of my data. I'm leaving this on purpose like this because maybe later, if we have the time, or if some of you want to, you can actually try to infer the errors from the observations. And if you read the paper that I have sent you a few days ago, or a few weeks, last week actually, fitting a model to the data by David Hogg and collaborators, you will see that these things are possible, that you can infer the noise from your data. And then finally, I have my my priors on. I have my posterior, which is just going to be sum of my prior and likelihood, because in principle it should be product, but since now we are in the log scale, it's going to be the sum. And keep in mind, what is the Bayes theorem saying? Bayes theorem is saying that posterior probability is equal to the prior probability times likelihood dividing by that normalizing factor. Since normalizing factor here is same for all the combinations of parameters, I'm ignoring it. So I never have to calculate explicitly the value of my posterior probability. I just have to find where it reaches the maximum. Okay? And now we're going to start sampling. And here is where the interesting thing comes. So basically, this package works in the following way. First, we're going to define number of dimensions, and the number of dimensions in this case is 2, because we have 2 parameters. So our walkers, as they are called, are going to walk through two-dimensional space. Then this specific Markov Chain Monte Carlo method is a little bit more advanced. I chose to use it because it's well tested and it works really well. In principle, if you're writing your own, you're probably going to only have 1 walker, and it's going to be really simple. Here they use some tricks to make these so-called walkers, which are basically points that are walking through the parameter space. They're making them communicate, and they're accelerating the convergence that way. And then I'm going to define these quantities, which is X data, Y data, and errors. And I'm going to call I'm going to just change this according to quantities that we had before. No, it was up to 50, 10, 50. Oh, sorry. 3, right? Here we have 40. And the errors. What are the errors? Errors are our uncertainties. So it's basically Gaussian spread of our noise. And that is something that I'm going to show you how to specifically determine in a bit. For now, let's just go back and look at our Stokes V, because we are interested in the noise in the Stokes V, and let's try to estimate it. So in principle, it's relatively hard to estimate it by the eye here, but I was very conservative, and I said that noise is roughly 100. It's probably less than 100, but let's use 100 now, and we'll see what happens later. I also want to make a point there. In principle, this is a bad example, because in principle, di over d lambda also has noise. And for the homework, you will have probably to repeat this, including noise in di over d lambda, which means including noise in both axes. But here we are only including noise in this axis here. Cool. So what I'm doing now is I'm defining these quantities, and then the way I initialize first I need to initialize starting parameters for each of these walkers. And you might want to spend some time to study these. Basically, starting parameters are starting positions. So the only thing that I'm doing here is I'm basically picking 100 random numbers for the location of these points. In principle, you might want to fit using some other method first and then randomize around that point or something like that. Doesn't matter, it's going to work anyway. Okay? Then what I'm going to do is I'm going to initialize the sampler using something like this. So sampler is MC ensemble sampler, which has n walkers, which is 50 for us, 2 dimensions, okay, which is 50 for us. The function that it's using to sample, it's sampling the function called ln posterior, okay? So it's finding the maximum of the log of the posterior. And the arguments are x data, y data, and errors. So these are basically measuring quantities that are used to calculate our posterior. So let's go back and take a look here. So posterior is a function of parameters, x, y, and error. X, y, and error are always going to be the same, only the parameters are going to change. I mean, for one given data set. And that's why we say that we are walking through two-dimensional space of the parameters. And then finally, we can run our sampler, and it's going to do something. I'm going to separate this, okay? We're going to run our sample for 1,000 steps, which means each of these 50 walkers is going to make 1,000 steps. So we're going to make 50. We're going to end up with 50,000. No, sorry, 50,000 different positions in the parameter space. And when I run that, nothing happens, right? We have a star. Something is being done. We don't know what. So now we need to plot something. And now what I'm going to plot is all these quantities, all the positions where your things were walking are saved in the quantity called chain. And chain is, actually, let's do that first. So insert cell above. So if I do something like MP, or I can do sampler chain shape. So it has dimensions 50 for 50 walkers, 1,000 for 1,000 steps, 2 for 2 parameters, right? So what I'm going to plot now is I'm going to plot the chain, right? I'm going to plot different chains for these 2 different parameters. So basically, this is going to show me the paths of all the walkers, right? And if I do that, I'm going to get these fantastic plots. And these plots are basically telling me, so all the walkers started from some relatively random quantities that were between 0 and 1. So as you can see, the positions for the first coordinate, which is the slope, started randomly behind 0 and 1, but all walkers very quickly, already after 100 steps, converged to some point which was close to 0. If you remember, the real value was 0.004, something like that. Okay, so we would have to zoom to see what is really happening here, but only the thing that I want to show you is that all the walkers started far away from this and converged to the real place. On the contrary, for the slope, and this is because we were not taking care about the magnitude of our parameters, we started from somewhere between 0 and 1, which we can't even see that, and we see that they spread and they were sampling this place somewhere around between minus 50 and 50, right? So now if I zoomed this point here, and I'm going to do this this first one, I'm going to say plot y range, no, it's y lim, let's say 0, 0.01. No, minus 0.01, 0.01. You see now that that value is somewhere around minus 0.005 or somewhere like that. Okay. So what I'm going to do now is I'm going to immediately show you the results, and then we're going to go back and deconstruct it a little bit. If you just do sampler flat chain, it's going to return you all walkers stacked upon each other, and then I can use this super convenient function corner to immediately produce a corner plot. And what we want to do, and actually now we're not going to do that. If I just plot it like this, I don't see many useful things because it's completely tracking the paths of these walkers wherever they were walking. However, you might notice that actually we are not so interested in this first part of walkers roaming around, right? because it took them some time to find where the maximum was and then to walk around the maximum. Does that make sense? Somebody should say something so that I don't feel completely lonely here. Okay, Niraj, you have experience with this. Does this make sense?
I think Niraj left.
Niraj left. Does it make sense? Does it make sense to you then? Okay,
Makes
cool.
sense to me.
Oh, okay, cool. Nice to hear that. So what I'm going to do is I'm going to use something called burn-in. And the simplest possible way to do this burn-in is just to skip certain amount of samples that you did. And the way that I'm going to do it, so keep in mind that this flat chain now has 50 times 1,000, so it has 50,000 samples. I'm just going to skip first 10%. And I'm going to repeat what I did here. And if I do that, bam, look at this triangle plot or corner plot. So what we see now is basically in this scatter plot, in this density plot, we see the positions of the walkers skipping first 50,000 positions. We see where they were, and we see this distribution basically of the posterior, of the posterior, and we see which combinations are more likely, which are less likely. And now these two histograms are basically what we called, if you remember from the last week, marginalizations. So let's add a comment here. So recall that marginalization. Actually, maybe I already have that down there somewhere. No. That marginalization works like this. So P of K, we are interested in slope, right, is integral over the whole space. P of Kn. And I'm going to be precise, and I'm going to use this given the data, because we are talking about posteriors here. The N, right? And now I need something like this. So remember that here, in principle, what we wanted to do is we wanted to know the slope, because we wanted to know the magnetic field. And the slope, we wanted to know the slope given the data. So this left-hand side here is the posterior distribution of the slopes given the data. But what we are fitting for, we are fitting with the linear function, which has two parameters. And what we want to do is basically we want to marginalize over this parameter n. And this sampling, because sampling somehow immediately gives us the integrals, this sampling is basically saying, oh, well, you know, this function here, pkn given d, is greater where I have more points. So the only thing that I have to do is basically to plot histograms over this one axis that I'm interested in, ignoring the other axis, and that's going to be my marginalization. So basically what we are interested in here is this histogram up here, the histogram of the slope, okay? And this is from where we can see, for example, oh, wow, well, it could be that this doesn't look Gaussian, that this has multiple peaks, that this is asymmetric, or so on and so on, because keep in mind that the posterior doesn't have to be so complicated. It doesn't have to be so simple as it is here. It can be much more complicated. Okay. So then what I'm going to do next is I'm just going to squeeze the numbers of parameters that I'm interested in. I'm going to do, actually, I'm not sure whether I need MP squeeze here, but I do just in case. So I'm just going to take all these members from the chain except the first 5,000. And what I'm getting then is I'm getting an array which has 45,000, which is 45,000 positions at 2 coordinates. And then if I just plot the histogram over the first coordinate, which is the slope, I'm basically going to get the same histogram as I was getting up here, right? But now comes the real advantage of this thing is that we can finally, we can now estimate errors or uncertainties or confidence interval for our quantity that we were measuring. And keep in mind that this histogram here is basically your a posteriori probability density distribution for your parameter. So this is the probability of some value being a true value of your slope given the data, right? So one of the ways, now it's up to you to decide what you want to show, but one of the ways to now choose what you want to do is to say, well, okay, I want my, let's say, 95% confidence interval, which would be something like 2 sigma. So what I'm going to do is I'm going to say, I'm going to cut 2.5% of the left-hand side, 2.5% of the right-hand side, and I'm going to find the median, and I'm going to report that. So in practice, you would use that using this percentile function in NumPy. So you provide the array that you're dealing with. So here I'm just providing the array containing the slopes, and I have limits. So I'm interested in the position of where 2.5% of the distribution are, where 50% of the distribution are, which is the median, and 97.5. And then I'm going to translate these into some values of the magnetic field. So we need 67 here, I'm sorry. And I'm gonna run that now. And what I'm gonna print is, oh, sorry, I didn't want this to happen. What was this? Hop, 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 hop. Okay, now it's fixed. I forgot to run one of these. So now what I'm getting is I'm getting my median value, right? Which is 150. I'm getting my, so let's get rid of this just so that things are more clear. I'm getting my lower confidence value, which is 136.88. And I have my upper limit, which is 164.11. And then usual way to report this is you calculate these differences, and then you input them here. So this would be, so let's always round up to higher values. So this would be something like 14. If you are confident enough that you want two, how do you say that in English? If you want 2 digits, yeah. But in principle, you could just say 150 plus minus 20 Gauss here would be reasonable. And this process is going to give you these upper and lower errors very, very reliably. And this is what most of the people are going to do when they have a relatively simple model, but when they want to assess all the uncertainties and all the correlations very carefully. So for example, people in cosmology who are determining cosmological parameters are doing this. People who do detection of the dark matter using supernova do this, and so on and so on. Now the problem is, of course, that if we wanted to do this for every pixel, it would be very slow, right? And you can try and do this for every pixel, and actually maybe with today's computers it will work, but keep in mind that for this we needed to calculate our posterior, this function here, which basically relies on this function here, which is called likelihood, which is calling our model here. We had to calculate it 50 times 1,000 times. So we need to calculate 50,000 times. Now imagine if you have a complicated forward model, such as, for example, line formation that we did in the last class. Imagine running all that 50,000 times just to diagnose quantities at 1 pixel. That's really, really dramatic. That's very hard. And that's why you can use these methods to infer something very carefully and to probe some things and to try and understand what is going on. But it's very hard to use Markov Chain Monte Carlo for huge amounts of data. But still, this is something that I think you should really, really know. So that's why I spent so much time talking about it. Okay, something that is very nice to plot, I'm going to leave you to do it on your own, is to just, for example, now we can take a few hundred random samples from our chain, okay? And we can plot them all on the plot to basically see how our linear functions are distributed. So to see which are the more probable and which are the less probable values. And now I need to go through all this again. Sorry about that. But I always like to change something when we enter the actual class. So let's see how this works. So what I'm doing here is I'm plotting you can't actually see now the fit, it's the thick orange line, is the best fit, where for the best fit I took medians of both of these parameters. You don't have to take medians. You can by hand, for example, find literally the maximum of of the distribution here and take that as your true solution, or whatever you think is the most appropriate. Just make sure to report this whenever you're writing a paper or whatever you're doing. And here I'm plotting these 200 randomly chosen things from the slope, and you basically see in which range our linear fits are living here. And this is very nice to do. Okay. But now, however, let's go back to the noise, because the crucial thing here is that given the noise of our data, this is giving us uncertainties on the parameters. And you are somehow already feeling that if the noise was smaller, my distribution would be more narrow, right?
Ivan?
Yeah.
So we did assume something about the noise when we're sampling our phase space.
Yeah, we assumed in this case that noise is Gaussian. So if the noise is Gaussian, then it means that I can write my likelihood through my chi-square. So yes, we assume that the noise is Gaussian and that we know the value.
So you really need to know your detector, what noise it's going to produce if it's not correlated or something, I guess.
That's excellent remark. Yeah, in principle.
Because I was just gonna chime in that like the Bayesian approaches are not like panacea for all everything. You can't just like marginalize like over everything in your experiment and just be like, oh, that's the posterior, right? Like you still need to understand very well the distribution of the noise you're working with.
Yeah. For example, if the noise here was correlated, we wouldn't have individual value for each valent. We would have the correlation matrix, right?
Yeah, I was going to ask about it because I've never done this before.
Me neither. In spectropolarimetry, we usually don't assume that. We should talk to somebody and see what's happening there, right? Because we really need to think where the noise comes from, right? The noise comes from the stochasticity of photons themselves, right? So it means that it comes from the sun, doesn't it? It comes because it's a random process, right?
Well, if you assume that you don't have any problems with your modulation system or something.
Yeah, I mean, this is the noise that I'm talking about here is the random noise, is the something that comes from the precision, right? Yeah. If you had the systematic effects, then modeling them would be harder, but you can still do that. And if you read again, we don't have so much time to go through all these things now, but there is an amazing approach where you can even detect the outliers. So you could even put some like very rough model for your outliers, and your fitting code would be able to tell you, oh wow, this pixel, there's something weird with this pixel. Mm-hmm. There is very low probability that this pixel really gave I don't know 6 sigma value outside of expected. Something is wrong with this. This is outlier somehow, and it would know how to eliminate.
Okay.
Yeah, we can all take a look. If you want, we can talk about this paper in one of our journal clubs. I would love to do that. It's a great paper, and it really teaches you all these methods. Mm-hmm. There. So now, where were we? We were back here talking about the noise. So, however, I just basically slammed the value from the noise, right? I didn't really determine it very well. So what I want us to do now is I want us to go back and to figure out what actually noise in the HINODE cube is, right? And basically that's the only thing that was sort of ad hoc here. Well, at least to me. Maybe I ran through some things very quickly with you, so you don't. So things are also ad hoc for you. But let's try and infer the noise. And how are we going to infer the noise? Well, we know that Stokes V in the continuum should be 0, right? So these oscillations here that are appearing in Stokes V are just the oscillations of basically oscillations of the because remember that Stokes V is a differential quantity, is I plus V minus I minus V, and I plus V and I minus V are some quantities that are separate, so they have different realizations of the noise in them. So when I subtract them and divide by 2, basically what I see here is the photon noise. in the continuum of the Stokes V. Does it make sense? Right, so the reason why Stokes V is going up and down here in the continuum is simply because I have different particular realizations of the noise in I plus V and I minus V, and then when I subtracted them, I realize this. We can even simulate that. I can send you a small piece of code which simulates that. So what I'm gonna do now is I'm gonna do the following thing. I'm gonna say, well, okay, since I plus V, I minus V, V is small, I plus V, I minus V are basically I. We already sort of relied on that. This noise in Stokes V should be roughly the same noise as sits in the Stokes I. So what I'm going to do now is I'm just going to take here, I'm going to take 100 times 100 pixel patch. I'm going to take last 10 points in the spectrum because I know these are the continuum, and I'm going to scatter plot them. And when I do that, I get a scatter plot like this. And you see that really the values are roughly centered around 0, but they have some spread. And we are actually gonna plot the spread now on the histogram. So what I also want to do is I want to plot the histogram from that. So insert cell below. So let's plot histogram. Is it just histogram? And let's say bins equal 100. No, it's hist. And that histogram looks like this. There are some values missing. I think this is because of the integers, but you see that the shape of this is very Gaussian. So Stokes V is really distributed as Gaussian. And then when I find the standard deviation of this, right, this standard deviation is going to be actually much smaller than 100. It's going to be something like 37. And then, since actually what our code wants, our code doesn't want the standard deviation. Our code wants standard deviation divided by square root of 2, right? Remember how I defined the different things? Actually, the standard deviation is. Oh, now I'm sort of. Okay, I'm going to test this, whether we need to divide this by square root of 2 or not. I'm not 100% sure, but since we're running out of time, let's go through this. I'm going to calculate. I'm now going to use the errors that result from this scatter here. I'm going to rerun my sampler. I'm going to now calculate the spreads, and now you maybe, if you remember the quantities, you see that now these spreads of the posteriors are much, much more narrow. And the way to convince ourselves of that is to calculate the errors. And now we have basically the same value. So the maximum is still going to be more or less the same. It's going to vary very, very slightly because these are random processes, but the uncertainties are much smaller now. Remember, they were like 13, 14, now they're 3.5. So the smaller my error is, more narrow my posterior distribution is, and that's why it's very important to know your errors. Okay, and this is something that you can apply to whatever you want. So now you can do various kind of inference for various kind of things using this, and it's not, of course, this is for me, the main strength of this is that this is definitely not limited to linear models. You can use as complicated model as you want. So you can plug the line formation process up here in your posterior or whatever you want. It's just that you're going to have to wait much, much more. But this is going to show you various kind of things. And if you remember, I have shown you a few weeks ago, I have shown you the okay, let's go back to one of the corner plots, for example. This one, I have shown you the way where these plots don't have to be nice circles like this. So they can be either tilted, indicating some correlation between the parameters, or like really be these twisted banana shapes which illustrate that the parameters are, you know, seriously degenerate and live on some very weird chi-square surfaces, and so on and so on. Okay, questions, comments, problems? Okay, if not, then I'm just going to very briefly show you something which I couldn't make work for Python 3, and that's the reason why we didn't spend time doing that today. And that is the Milne-Eddington synthesizer. So if you still have Python 2, which is probably funny of me to ask, because I'm the person who claimed to Python 2 way longer than he was supposed to. But if you have Python 2, then this Milne package that I have sent you in an email, you will be able to install it. For some reason, it doesn't work for Python 3 for me. Please try to install it. Let me know if it works for Python 3 for you. If yes, you can show me how to install it myself. If no, we can get in touch with Andres and ask him how it works. But this allows you to use a little bit more realistic line formation model, and actually this is this so-called Milne-Eddington approximation, which we were supposed to devote full workshop to sometimes in April. Of course, that's canceled now, but it will happen at some point. And I have shown you in the previous Thursday how it works in the online widget. Now you can install it and run it in Python here. It's very easy. You just specify your line wavelength, J upper, J lower, angular quantum numbers, G upper, G lower, which are lambda factors. What we worked with in weak field approximation were not level lambda factors. These were equivalent lambda factors, which characterize transition as such. Then you have to define your wavelength grid, which is going to contain starting wavelength, steps, number of wavelengths, and then you put these things into this quantity called line info. And then you define your model. So these things describe your line, right? This is your line model, so to speak. These things up there, they describe your atmosphere. So there is magnetic field inclination, magnetic field azimuth, macro turbulent velocity, damping. B1 and B0 and B1 are these two parameters describing the slope of the source function. Mu is the position on the limb, so we usually want mu equals 1. Doppler width here, and KL is the strength of the line. And then you define that as the model, and then you just define this S, which is like object. And then if you do S synth, it will return you Stokes parameter. And what we can do now is we can just run that. It might be even here, yeah. So if I just run Milne-Eddington demo, I don't know, I have to do Python 2. Me demo. It's going to run something, and now I can open the image, and here it comes, and you get the Stokes profiles corresponding to your model atmosphere. So just to convince you that this is not some Stokes profile that I just pulled out of some hard drive, I'm going to increase, for example, the magnetic field to 1000. And I'm gonna change B1 and B2 to like B 0.3 and 0.7. And I'm gonna rerun. And now my line is much deeper because I changed the slope. And my Stokes V, Q, and U are much stronger because I increased the magnetic field. And you can now, if you manage to install this, now basically what you can do is you can write your own Milne-Eddington inversion using this, because now this is going to be your function that determines your posterior. You can't use the linear solution because Milne-Eddington is not a linear model. But what you could use, for example, is you could define, for example, chi-square, and then you could use some minimization procedures from SciPy. For example, there is SciPy optimize minimize, which works fairly well, and it has options for using various ways to find the optimum solution, and so on and so on. So the only unfortunate part is that this doesn't work for me yet in Python 3. I will try to make it work, and if it works, then I will make a small Python notebook for you and just send it to you so you can see how Milne-Eddington inversion would proceed in this case. So in this case, we have much more free parameters. In principle, all these, okay, except mu. Mu is determined by our observations. All these are the parameters that we fit for. And now we don't have only one measure. Basically, we instead of just looking at V, we are looking at both Q, U, V, and I. And we are determining all these parameters there. Okay? And this is already very, very powerful because it can tell you the full vector of the magnetic field. And it is still used for many missions and many instruments in many cases. Like the default HINODE data inversion module is Milne-Eddington module. So that was everything for today. Any questions and comments now? No. Okay. Well, in that case, see whoever is interested, drop by on this Zoom tomorrow around 1. I'm going to show you how non-LT two-level atom works. In the meantime, play with this. Try to figure out some things to do if you want. Stay safe, stay healthy, stay warm because it's snowing now. And yeah, I'll see you all real quick. And if you have any questions, if you have any comments, just write to me or call me on Zoom. I'm gonna go and get some water and stretch my legs. I'm gonna stay online if anybody wants to ask anything or just chit chat. So I'll leave everything on. I'll just stop recording. I'll stop sharing, and then we can talk if you want. If no, then see you soon.